So in this video, we're going to start to talk about when the octet rule falls apart. So as a reminder, the octet is that each element has 8 electrons, with the exception of hydrogen that has 2. So it has its own octet. But the question is, how can we look at octet? And when does it fall apart? So there are 3 ways. We have an odd number of electrons, we have less than octet, or we have more than octet. So let's look at odd electron species first. So they have an odd number of electrons, and they can't have octet, because if you have an odd number, someone will have less than 8. So for NO and NO2, the valence electrons here are 5 plus 6, and that gives you 11. So you could create 2 structures, NO or you could draw a structure that looks like this. So the difference between these 2 structures, it has the same 11 electrons, but they either have a lone electron on the nitrogen or a lone electron on the oxygen. So let's look at the formal charge. So if we look at the molecule, we're going to start with the nitrogen for the top compound or the bottom compound. So nitrogen in this case is 5 minus half of 4 minus 3, and that gives me 0. For oxygen, it is 6 minus half of 4 minus 4, also 0. If we look at the one on the bottom, nitrogen is 5 minus half of 4 minus 4, which is negative 1. And oxygen is 6 minus half of 4 minus 3, which is plus 1. So in this structure, we have the more electronegative atom being positive and 2 charges. So NO, with a single valence electron on the nitrogen, is preferred. So for NO2, it also has 2. It will have an odd number of electrons. 5 plus 2 times 6 is going to give you 17. And so you can draw these structures, and the 2 different structures are this. Where there is a single dot or single electron on the nitrogen, so we have a positive charge and a negative charge. And so it will have a resonance structure with this orientation. And so in an odd electron species, the goal is to create a structure with minimal formal charges and the odd electron being in a place where it is advantageous to formal charges. So let's look at less than octet. So in terms of less than octet, BF3 has the valence electrons of 3 plus 3 times 7, that gives us 24. So if we follow the rules, put the boron in the center, connect to our 3 Fs, add our lone pairs. So as we add these lone pairs, which will take just a second, we've now used all 24 of our electrons, but boron does not have octet. So the rules state that we're going to take one of these pairs and go here. So we have boron, fluorine, fluorine, fluorine. We'll go ahead and add our lone pairs back. So let's calculate the formal charges, because you should get in the habit. So boron is 3 minus half of 8, and that gives you negative 1. And for fluorine, down here at the bottom, it's F minus 7 minus half of 4 minus 4, and that gives you plus 1. So this structure has a positive charge on the most electronegative atom. So this is non-preferred. But if we look at the structure over here, and I'll come in and erase this circle real fast. So let's look at the formal charges of these atoms. So boron is 3 minus half of 6 equals 0. and all of the fluorine atoms look the same, so it is 7 minus half of 2 minus 6, and that also equals 0. So we see less than octet, but no formal charges, and so that is a preferred structure. We can see less than octet for boron and all other elements in that column, such as aluminum, gallium, indium, and thallium, as well as alkali and alkali earth metals. So when we think about things like sodium or magnesium or beryllium, which can make covalent like bonds, we can see that they are content to have less than octet. So let's look at more than octet. So elements in the third row and below can utilize their d orbitals. So if we were to look in the p block elements, where we have carbon, nitrogen, oxygen, silicon, phosphorus, sulfur. This is the third row and below, but we really only see it for phosphorus, sulfur, chlorine, arsenic, selenium, beryllium. So anything in this part of the periodic table can expand their octet because they have access to d orbitals, and they can expand to 10 or 12 electrons. So let's look at As5, or arsenic pentafluoride. So the valence electrons is 5 plus 5 times 7, and that's 40. So if we follow the rules where we put the arsenic in the center, and we connect, should be an S, sorry about that, and we connect these fluorines, before we even add any lone pairs, arsenic has 10 electrons around it. But once we add all of our lone pairs to these fluorine atoms, there are no additional atoms or electrons that need to go onto the central atom. So in this case, what we can see is that we're going to look at our formal charges. So for arsenic, it's 5 minus half of 10, so that's 0. And fluorine is 7 minus half of 2 minus 6, also 0. So this is a preferred structure, it just has more than octet. So let's look at sulfur hexafluoride. So the valence electrons are 6 plus 6 times 7, that equals 48. We're going to put our sulfur in the center. We're going to carefully connect 6 different fluorines to it. And then we'll see, what we'll see is that we can put all of our valence electrons, and then we will have used all 48 of our valence electrons. So sulfur is 6 minus half of 12, and that's 0. And fluorine is 7 minus half of 2 minus 6, also 0. So in both of these, they have more than octet, but their formal charges are all 0. Let's look at some other examples. So for XeF2, so we have 8 valence electrons plus 2 times 7, which is 14, and that's 22. So we'll put our xenon in the center, connect to 2 fluorines. We're going to add octet here. So now we've used 16 of our 22 electrons. So 2, 4, 6. So now we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So they're all there. Our formal charge for xenon is 8 minus half of 4 minus 6, and that equals 0. And fluorine, as we know, is F minus 7 minus half of 2 minus 6, also 0. So xenon has more than octet, but based on its location, it can't. So let's see what happens if we add 2 more fluorines. So we have 8 plus 4 times 7, and that equals 36 valence electrons. And so we'll put our xenon in the center. We're going to go ahead and add our 4 fluorines. And so as we use these up, so 4 times 8 is 32. So there are 4 electrons left over, which we will add here. So fluorine looks the same, so we don't need to think about its formal charge, but xenon is 8 minus half of 8 minus 4, which is 0. So even though it has 12 electrons around it, it's still a valid structure. So let's look at aluminum trichloride. The valence electrons are 3 plus 3 times 7. So that's going to give us 24. We'll put our aluminum in the center, connect to our 3 chlorines. As we add the valence electrons to each chlorine, we note that we've used all 24 electrons. But based on the location in the periodic table, aluminum can violate octet by not having enough. So it would be 3 minus half of 6, and that equals 0. So elements in the third column, meaning the one with boron, aluminum, gallium, can have less than octet. Elements in the third period, so the third row on the far right side, can have expanded octet. And so they still need to follow the formal charge rules, but otherwise we can start to think about elements or compounds without octet.